Now, how can we use the apparatus? We were actually doing this thing where there was a magnet, a strong magnet on the top of an electronic balance. And when current passed through it, the reading on the electronic balance was changing. And we want to use this apparatus to find out the magnitude of the force on the current carrying conductor. So how can we use this apparatus to find out the force on the current carrying conductor in the magnetic field? Now, what we can do is we set apparatus as shown in the diagram. Now we change the reading on electronic balance to zero. This thing is called tearing. We tear the electronic balance. Like we put the magnet on, and obviously when we were putting the magnet on, the reading on the electronic balance will change, and it will be showing the mass of the magnet on the top. What we do is we just press the tear button on the electronic balance, and when we put that tear button, it will make the reading zero. Now the magnet on the top has zero mass. Any additional change, like if we put anything else now, electronic balance will only show the reading of that new thing on the top. Now we change the reading on the electronic balance to zero when we uh, close the switch. When we close the switch, electronic balance shows a reading of mass. Remember, positive reading means magnet pushes the wire up, and negative reading means magnet pulls the wire down. So listen, look, if magnet pushes the wire up, as a reaction, wire will push the magnet down. And when wire will push the magnet down, the reading on the electronic balance will increase. It means that if magnet is pushing the wire up, the reading on the electronic balance should increase. And if magnet pulls the wire down, when magnet pulls the wire down, wire will pull the magnet up. So in that case, the reading on the electronic balance will decrease. So if there is a positive reading, it means the magnet is pushing the wire up. And if there is a negative reading, it means the wire is pulling the magnet down. And even if you do not tear the electronic balance, you just let the reading be, and you want to go that reading one, reading two, reading two minus reading one kind of thing. In that case, if reading increases, it means the magnet is pushing the wire up. And if reading decreases, it means magnet is pulling the wire down. So when we close the switch, the electronic balance shows a reading of mass. Now we can use W equals to mg to find equivalent force experienced by the wire. So this is how we can use this apparatus to find out the size of force exerted by the magnet on the current carrying conductor. Now, let me shift this thing a little up. Okay. Now, this is how we can use this apparatus to find um, force on a current carrying conductor. Now, the next thing is, what are the factors that affect the size of force on the current carrying conductor? Question. List all factors that affect size of force on current carrying conductor in a magnetic field. Now, now this is the same apparatus. Okay, this is the same apparatus. Now, what are the factors that affect the size of force on the current carrying conductor? Number one, force on conductor depends on number one, magnetic flux density. Okay, this is the proper name. You can also, like, if you're mentioning that, mentioning it as a factor, you can also call it strength of magnetic field. But the proper name of the quantity that we will be using, the formula will be magnetic flux density. Force is directly proportional to magnetic flux density. If you use a stronger magnetic flux density, you will have more force. If you double the magnetic flux density, you will get double force. So there is a numeric ratio between force and magnetic flux density and fixed numeric ratio between them. Now, second thing is magnitude of current. More current, more magnetic field. of the current, hence more force. Remember why there is a force on a current carrying conductor? Because current carrying conductor has its own magnetic field and permanent magnet has its own magnetic field. When two magnetic fields mix together, they exert force on one another. And this is why the current carrying conductor experiences force. Now, if there will be a stronger current, there will definitely be more magnetic field because of the current. Hence, there will be more force. Now, third, length of, or I should say, effective length of conductor in magnetic field. Listen, it does not mean how long the conductor is. For example, if X and Y are 2 points on the conductor, the length will not be from X to Y. Actually, we will only be looking at the length, which is the length of the conductor inside the magnetic field will be considered as effective length. It is not the length of the conductor, but the overlapping length of the conductor in the magnetic field. So force is directly proportional to length.
Excuse me, sir.
Fourth, did you say something? I couldn't hear you.
So, like, while giving the current on the wire, like, do we have the same magnetic field throughout the wire in all the throughout the length?
Mhm.
I mean, like,
I could not.
जब हम
Yes.
करंट पास करते हैं ना वायर में, वो
Mm-hmm.
मैग्नेटिक फील्ड जब बनाता है ना, वो मैग्नेटिक फील्ड नहीं, मैग्नेटिक फोर्स जो बनाता है वो वायर
Uh-huh.
करंट के कारण, तो वो मैग्नेटिक फोर्स वो वायर के सभी भाग में होगा कि कुछ स्पेसिफिक?
नहीं नहीं नहीं, वो उसके पूरे पूरे के पूरे बॉडी में होगा करंट कैरिंग कंडक्टर के. लाइक from point X to Y, if there is a current that passes through from point Y to point X, it will have a magnetic field all around it from Y to X. But only the part that is inside the magnetic field will experience force.
ओके सर, गॉट इट.
I hope you understand कि अगर एक मैग्नेट आप कहीं रख देते हो ना, you won't find it experiencing force because of itself. A simple current carrying conductor has a magnetic field, but the problem is there's not another magnetic field to to affect it. But when the current carrying conductor passes through another magnet, as shown in the diagram, then in that region there will be a force experienced by that current carrying conductor. If we have that region very long, there will be more force. If that region is small, there will be smaller force. Mhm.
ओके सर, आई गॉट इट.
Good. Now, the last thing that in the list is force also depends on angle between conductor and magnetic field. If magnetic field and current are parallel, no force. force becomes zero. If magnetic field and current are perpendicular, force is maximum. Okay, so it depends on angle between the conductor and the magnetic flux density. So what is what is the trigonometric ratio that is zero when angle is zero, and that is maximum when angle is 90? Answer is sine theta. So that means force is directly proportional to sine theta. Did you say something, Hassan? Okay, I couldn't hear you again. Now, so these are the four factors that affect the size of force on a current carrying conductor in a magnetic field. Number one, how strong the magnetic field is, magnetic flux density. Number two, how big is the current? More current, more force. How long the conductor stays inside the magnetic field. If it stays for a smaller length, then there will be smaller force. If there is a longer length of conductor inside the magnetic field, there will be more force. Now, all these things are directly proportional to force. That means force is directly proportional to magnetic flux density, current, length, and sine theta. So if I have to make it equal, like if I have to make an equation, then it has to be F equals to N B I L sine theta, where N is number of turns of wire or coil. Like, listen, for the example that we are discussing right now, this is a magnet. Okay, this is a magnet, and the wire is just going like this once, and then connected to the battery and everything here. Like, there is a possibility that instead of connecting the wire like this, what we do is we make the wire complete many turns, like multiple times the wire passes through the magnetic field, and then we connect it to the battery like this. Okay, for example, there are n times this is going, so that means that n wires separately will experience the same force. The force will become n times more. So if we use more coils, then we can also increase the number of turns. So the force is directly proportional to n, it is directly proportional to b, it is directly proportional to I, it is directly proportional to L, and it is directly proportional to sine theta. So this is a very important formula. Okay, so now
Sir, is
let's
this
talk.
formula also applicable in transformer?
No, no, it is not.
Okay.
I know what makes you say that. I think when I said number of turns, you remembered those things that you have done that in transformer, number of turns of the coil.
Yes, primary coil and secondary or something like that.
Okay, okay, okay. That is an opposite phenomenon of this thing, but it resembles a lot. It resembles a lot, and we will discuss that in a like I hope like I don't think in today's lesson, but hopefully in next or lesson next then next we will be discussing that.
Okay, sir.
F equals to N B I L sine theta. Units are very important. Force has to be in newtons. N, no unit, it is a number. B is in Teslas. I must be in amperes. L has to be in meters. So sine theta has no unit. Okay. We will be using this thing to define Tesla. So pay attention over here. Okay. A very uh, frequent question. I call these questions examiner's favorite question. One of the examiner's favorite question is, what is meant by one, what is meant by Tesla? A 3-mark question. Answer. Magnetic flux density is 1 Tesla if a force of 1 Newton is experienced by a unit length of conductor carrying 1 ampere of current perpendicular to magnetic field. Now, apparently, this seems very complex statement. You can come up with this different statement as well, but here is a secret for this one. If you remember, there was a formula F equals to BIL sine theta. I'm talking about just one coil, so I don't need N here. If I make B the subject of formula, it becomes F equals to, B equals to F over I L sine theta. So remember, magnetic flux density is 1 Tesla. If force is 1 Newton, current is 1 ampere, length is 1 meter, and sine theta is 1. Sine theta is 1 when theta equals to 90 degrees. Okay? So you have to put all this in one sentence. That you have to mention that magnetic flux density will be 1 Tesla if a force of 1 Newton is experienced by a current of 1 ampere in a length of 1 meter of wire when passing through the magnetic field at 90 degrees. So you can come up with any sentence that mentions that there is a force of 1 Newton on a current of 1 ampere in a length of 1 meter when it is perpendicular to the magnetic flux density. You have to put all these four things in one sentence, and if you do that, you get 3 marks. I hope you understand. Any confusion? It is a very common question. Examiner keeps on asking this thing, and you can put it in any sentence. But if you want to make your own sentence, it is recommended that you write it down and get it checked by me. But you have to come up with any sentence that mentions all these four things: force, current, length, and sine theta. They all should be one. Okay. Then magnetic flux density will be 1 Tesla. Now, direction of current carrying conductor, or direction of force on direction of force on current carrying conductor. Now, here we go.
Mr. going to use the left hand rule, fragments left hand rule.
Yes, actually, that is what I'm about to explain. So this is a U-shaped magnet. Okay, this is a U-shaped magnet. This is a north side. This is a south side.
South side.
So what is the point? What is the point of making a U-shaped magnet? Actually, this is a way we can get the north and the south magnet, south pole of a same magnet in front of one another. We don't need two magnets. We can generate a magnetic field using a single magnet. So this allows us to bend a bar magnet into a shape of a U, and this will help us to get a north and the south pole of a single magnet in front of one another. So now we have this uh, conductor that passes through the magnetic field, and there is a current that is going this way. There is a switch over here. So we this is point X, this is point Y,
Why?
and current is because look the battery. This side is the positive terminal. This side is negative terminal. So direction of current will be from positive to negative. So current will go
Yes.
from X towards Y. So in the rod, current will be going this way. So if we see from the reference here, Now, if there is a person looking at this scene from here, okay, this is an observer. So according to this observer, there will be north on the left, south on the right, and there will be a current going away from the observer.
Yes, from north to south.
No, 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 no. Magnetic field will from the north to south, but the current will be going away from the observer. So,
Yes,
for
yes, yes,
do
yeah,
you
yeah.
do you remember that
It's
we
going
did
to be
that
the
cross
X.
and
Yeah, 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 yeah.
X?
Remember the cross
Okay,
and
okay,
the point. Yeah.
yes, yes. So current is going away, so we will put a cross for that. It means according to the observer's point of view, current will be going away, and it will have a magnetic field around it. Because of this current, there will be a magnetic field. Just let me make it in the center. Now,
But sir, will the magnetic
so
field be
if we
what is the
use a right hand grip rule, we can understand that the magnetic field will be this way. Okay, just make one circle with just one arrow on top, one arrow at the bottom. Okay, there is a permanent magnetic field because of the permanent magnet, which will be like this here. So magnetic field lines will be little distorted because of the presence of the coil over there. Okay. So magnetic field of the permanent magnet, these black lines, they are showing the direction of magnetic field of permanent magnet. The blue arrows are showing the direction of magnetic field of the current carrying conductor. So what do you think? Is there a love or hate between these two magnetic fields?
I think it's love. It's because going in the same direction.
So do you think same magnetic fields love one another or they hate one another?
Though they hate one another, so they repel.
Oh, the black one will push the blue one down, and the blue one
Yeah,
will push the black one up.
up. Yeah.
Okay, there will be a repulsion between them.
Yes.
And we are talking about the force on the conductor. We are not talking about the force on the magnet. So
Yeah.
on the top, there should be a downward force on the conductor. Let's see what is happening on the lower side.
This is
The
typically a
black,
love relationship.
look, the lower side of the circle. The blue line is towards left, the blue magnetic field, and the black magnetic field is towards right. Is there a love scene between them or a hate?
Love.
These are two opposite magnetic fields. They are supposed to attract one another. So there will be a love. So black one will be pulling the blue one down. Okay. There is a downward force on the top. There is a downward force on the bottom. So overall, there will be A downward force. Does this make sense?
The force combination of both on
Yes.
magnetic field on and
No. Not on the magnetic field. On the current carrying conductor, there will be a downward force.
okay.
Okay. Now, pay attention. We cannot do all this to just find direction. There should be an easier way. So, can you look at your left hand palm? I have made the thumb a bit bigger. Okay, this is your left hand. Palm. What is this?
Left hand palm.
Okay, you make your left hand palm as flat as you can. Your thumb should be upright. Now, this palm is showing the direction of current. So current comes out of the palm. Your fingers are pointing along the direction of the magnetic field. And your thumb is giving it to the direction of force. Okay. So remember, current comes out of the palm. Fingers are direction of magnetic field. So they point from north to south. This thumb is showing you the direction of force. And current is the direction of the palm is the direction of current in the conductor. For example, look at this situation. What is the direction of magnetic field? According to the screen, is it towards right, left, up or down? Magnetic field from like it has to be from north to south. So will it be towards left, right, up or down? Magnetic field.
The permanent magnet or in the wire?
The permanent magnet. The permanent magnet.
From right to left. No, from
Like towards
from left
left.
to right. From left to right. From left
No,
to
no,
right.
no. Towards left. Or towards
Yes,
right.
towards the left.
Towards left or towards right. Just give me
towards
one.
the right.
Because remember, if you want to check the direction of magnetic field, just place a north pole of a magnet over there. If you put a north pole in between those two poles, will that north pole experience a force towards right or towards left?
It's going to experience towards the right.
So that means the magnetic field is towards the right.
Yes.
Okay, what is the direction of current? Is it going into the screen or coming out of the screen?
Into the screen.
Like right now, make your palm like you want to shake hand with somebody with left hand. Make your palm
Yeah.
flat. Make your thumb upright. Your palm should be facing the screen because the current is going into the screen. Your palm should be towards the screen. And while keeping your palm towards screen, make your fingers point towards south. Can you do that? Your palm right now, if you're looking at your laptop,
Yes.
with your left hand, your palm should be towards the screen and your fingers should be towards right. Let me know what your thumb is doing. What is the direction your thumb is pointing right now?
Upwards.
Okay, are you using your left hand or right hand?
Left hand.
And
My finger should be towards the.
Okay, just 1 second, 1 second. You're using your left hand, your palm is towards the screen,
Yes.
and your fingers are towards right, like towards the south.
Yes.
What is your thumb doing?
It's facing up.
What kind of left hand you have?
Mister, should my palm face me or
Like you know when I say your palm should be facing the screen, it is like you're saying hi. You're saying
okay,
hi
it's
to
downwards.
somebody in the screen. Sorry?
It's downwards. My thumb is downwards.
No. Yeah. No, it is not possible. You have to make me explain why it was pointing upward before.
You gave a savage reply, sir. What type of hand you are?
No, I was just joking. I think that
Yes,
I
I
hope
understand.
Hassan, listen. I want to understand what you are doing wrong. Why your thumb was pointing up?
Yes, yes.
Was your palm facing you instead of the screen, or you are using your right hand?
Yeah, yeah. It was facing me.
Oh, yeah, because the current is going into this. Look, current is going from X to Y. So your palm should be towards the screen. Okay, you should be looking at the back of your left hand. And when you turn your fingers towards south, your thumb should be pointing downward. And this is how you can find out the direction of force on a current carrying conductor in a magnetic field. Is it easy?
Yes, but
Okay. So tomorrow we will be doing more of these
but sir,
examples because
I remember
we'll,
I remember something else. There was a rule where you had to use one thumb and two fingers.
I don't like that because most of the time students mess up with the fingers, and when they are turning or rotating their hand, it is not very easy to move your hand with those fingers. Believe me, this palm rule is far more easier than that. All you have to do is just remember that the current is always going out of the palm and fingers are always pointing towards south. This will be far easier than that finger thing. Hope you understand.
Yes, yes.
Okay, we will resume from the same point tomorrow. Thank you very much. Take care.
Thank you very much, sir.
Sir, could you send the link after this?
Okay, I will.
Okay.
Just finding some time. I will send you all the links in one go.
Okay, sir. Thank you. Good night, sir.